Okay, today we will start our first online lecture. We'll continue talking about the silicate clay minerals from where we stopped last time. Fundamentals of layer silicate clay structures. Most important silicate clays are phyllosilicates. They have leaf-like or planar structure. That means leaf-like a sheet. They are comprised of two kinds of horizontal sheets. Silicate-dominated sheet. This kind of sheet consists of two planes of oxygen with mainly silicon in the spaces between the oxygens with its basic building block called the silica tetrahedron. So tetrahedron, tetrahedral sheet or silicate sheet. Aluminum and or magnesium dominated sheet with its basic building block called octahedron. The sheet is also called the octahedral sheet. So octahedron, octahedral sheet. It's important to notice here we said aluminum and or. So that means it can be either aluminum alone, magnesium alone, or a mixture of the two. The tetrahedron and octahedron. The tetrahedron unit is composed of one silicon atom surrounded by four oxygen atoms. So it's four-sided unit. That's where the name mean comes from. Tetra, four-sided unit. The octahedron unit is composed of an aluminum or magnesium ion surrounded by six oxygen atoms or hydroxyl groups, eight-sided unit. Again, octa, eight. So the eight-sided unit, eight faces, not from the number of oxygens surrounding the central atom, because here it's composed of an aluminum or magnesium surrounded by six oxygen atoms, but it has eight sides or eight faces. Just to show you how it looks, where it comes from and the shape, how it is. So this is the tetrahedral silicon in the center, and these are the four oxygens. And if you look at the faces, the base, this side, and one in the back. So that gives you four faces. And here the octahedral magnesium or aluminum, we have the central atom magnesium or aluminum surrounded by six oxygens to give you eight faces. The tetrahedral and octahedral sheets are the fundamental structural units of silicate clays. So 2 to 4 of these sheets may be stacked together in sandwich-like arrangements with adjacent sheets strongly bound together by sharing some of the same oxygen atoms. So we can have 2 to 4, the number will vary from 2 to 4 of these sheets, the tetrahedral and octahedral sheets, stacked on top of each other, and they are the ones that's different could be sandwiched, like a sandwich between the other sheets. Okay, adjacent means the one immediately next to it. The specific nature and combination of sheets in these layers vary from one type of clay to another and largely control the physical and chemical characteristics of them. So we will see as we go ahead, we will see and concentrate on how the type of sheets that it's made of and what's the end of each sheet will decide on the characteristic and the physical and chemical characteristics of these clay minerals. The relationships between planes, remember when we talked about planes of atoms in the sheets, then we have the sheets, tetrahedral and octahedral sheet, and then layers or the crystal unit. We will talk about it in a minute when we start talking about the clay minerals. Before we go on talking about the structure, let's talk about this important phenomenon. Of course, this is already you have studied this in the undergraduate, but I'm repeating this to you because it's very important you understand this and you can build on it later in your all other presentations and other things. During the weathering of rocks and minerals, many different elements are present in the weathering solution. So during the weathering, of course, here we're talking about the chemical weathering. As the clay minerals crystallize, cations of comparable size may substitute for silicon, aluminum, and magnesium ions in the respective tetrahedral and octahedral sheet. What do we mean by respective tetrahedral sheet? Of course, if we are talking about substitution of silicon, silicon is found in the tetrahedral sheet, so it comes first. That means as they are mentioned above. That's what they mean respective. Respective, that means silicon for the tetrahedral and the magnesium or aluminum for the octahedral. Aluminum is only slightly larger than silicon. Consequently, aluminum can fit into the center of the tetrahedron in the place of the silicon without much change in the basic structure of the crystal. That's why the substitution here, we said it has to be of comparable size. The size has to be very close to each other so that one can replace another. Not the same. We cannot say exact. Of course, it will be then the same ion, but comparable. It has to be very close so that the structure will not be distressed and it will be stable. Isomorphous substitution can also occur in the octahedral sheets. For example, iron and zinc ions are not much different in size from aluminum and magnesium ions. This process by which one element fills a position usually filled by another of similar size is called isomorphous substitution. This phenomenon is responsible for much of the variability in the nature of silicate clays. We will see when we study the individual silicate clays and how much and where is that substitution occurs. Isomorphous substitution is of vital importance, very important, because it is the primary source of both negative and positive charges of silicate clays. We will see how that happens in a minute. The magnesium ion is only slightly larger than the aluminum ion, but it has one less positive charge. Of course, magnesium is divalent, aluminum is trivalent. If a magnesium ion substitute for an aluminum, that means the magnesium takes the place of an aluminum in a dioctahedral sheet, there will be insufficient positive charges to balance the negative charges from the oxygen. Of course, the sheets are neutral. How is the neutrality, or how does it come about? That means the positive charges have to equal the negative charges. The negative charges come from oxygen. Positive charges come from the ions like magnesium or aluminum. So if the magnesium substitute an aluminum, 2 charges substitute 3 charges, so we don't have enough charges, positive charges, to balance the oxygen negative charges, so we'll end up into a negative charge. Hence, the result, lattice is left with a -1 net charge. Similarly, every aluminum that substitutes for a silicon in a tetrahedral sheet creates a net negative charge at the same side or at that side. So same thing, we don't have to waste time on it because it's exactly like the above example. Sorry. In a trioctahedral sheet, if an aluminum substitutes for the usual magnesium or iron, then a net positive charge is created. Here we have the opposite. A trivalent taking the place of divalent, that means we have an excess of positive charge, more than we need to neutralize the oxygen charges, so we end up with a net positive charge. Based on the number and arrangement of tetrahedral, silicon, and octahedral aluminum, magnesium, iron sheets contained in the crystal units, or layers. So the crystal unit or layer, from now on, they mean the same thing. Crystalline clays may be classed into two main groups. The one-to-one silicate clays, in which each layer contains one tetrahedral and one octahedral sheet. So always the first number is for tetrahedral, the second number for the octahedral sheets. So one-to-one, one tetrahedral sheet, one octahedral sheet. The 2-to-1 silicate clays, in which each layer or crystal unit has one octahedral sheet sandwiched between two tetrahedral sheets. So two tetrahedral sheets, one octahedral sheet. Where is that octahedral sheet? Sandwiched between the two tetrahedral sheets. Let's start with the one-to-one. The one-to-one silicate clays include kaolinite, halloysite, nacrite, and dickite. Sorry. Kaolinite is by far the most common in soils. When we say by far, that means a lot more than the rest of them. It's the most common one that we find in nature in most soils. Each kaolinite layer consists of one silicon tetrahedral sheet and one aluminum octahedral sheet, so 1-to-1. Because a kaolinite crystal layer consists of these two sheets, it exposes a plane of oxygen atoms on the bottom surface, but a plane of hydroxyls on the upper surface. This arrangement has two very important consequences. Okay, let's look at it. So you have tetrahedral, okay? Okay, so you have tetrahedral, that's an octahedral, this is tetrahedral, and here an octahedral. So the octahedral, remember we said it has hydroxyl group, and the tetrahedral has oxygen. So when a sheet of tetrahedral, which is mostly oxygen, comes close to the octahedral sheet, which has the OH, between them, how are they connected together in nature? By the hydrogen bonding. You have O and OH. This will form the hydrogen bonding. And what do we know about the hydrogen bonding? It's a very strong bond. Remember, don't mix between these external bonds and the bonds that are sharing electrons, sorry. So that's totally different. These are chemical permanent bonds. These are external bonds in nature that connect things together, but also they can be broken at some time. So we already talked about this. Go to the next slide. So what are the consequences because of what happened, that hydrogen bond between the tetrahedral and octahedral sheets? First, where the hydroxyl plane is exposed on the clay particle surface, removal or addition of hydrogen ions can produce either positive or negative charges depending on the pH of the soil. We will study this a little bit later. Also, I will review it, although you should have known all these in the undergraduate course. Exposed hydroxylated surface can also react with and strongly bind specific ions. We also cover this in the undergraduate course. Second, when the layers consisting of alternating tetrahedral and octahedral sheets are stacked on top of one another, the hydroxyls of the octahedral sheet in one layer are adjacent to the oxygens of the tetrahedral sheet of the next layer. Therefore, the adjacent layer are bound together by hydrogen bonding, which I have already talked about when I showed you the structure. Because of the interlayer hydrogen bonding, the structure of kaolinite is fixed. So that means they are held, the crystal units are held together so tight, they do not expand, they do not move away from each other when they are wet. And no expansion can occur between the layers when the clay is wetted. Remember, in nature, we have crystals. Crystals or micelles are made of so many crystal units or layers. So how are these layers attached to each other? In this particular type of clays, they are attached to each other by hydrogen bonding, which is very strong. So this hydrogen bonding that keeps them so strong does not allow them to expand. Cations and water do not enter between the structural layers of a one-to-one mineral particle. The effective surface of kaolinite is thus restricted to its outer faces or external surface areas. So between the layers or the crystallines, there are no exposed surfaces. So it does not have any internal surface. The only surface it has, a crystal of one-to-one of that type of kaolinite, it has only the top surface, the bottom surface, and the sides. So it does not have any internal surface. So the effective surface of kaolinite is thus, due to this, restricted to its outer faces or external surface area. And that is not very large surface area. This fact and the lack of significant isomorphous substitution in this mineral account for the relatively low net negative charge and small capacity of kaolinite to absorb exchangeable cations. Now, although they do put these facts together, let's remember that the isomorphous substitution is not something we can explain. We explain it, we describe it. This is how it happened in nature. We do not have anything and no control about how much isomorphous substitution in each clay mineral. That is part of its characteristic when it formed. So the isomorphous substitution is the reason or the cause of the negative charges. So how much isomorphous substitution, how much you have negative charge. This one does not have a whole lot, not very large substitution. So it has low isomorphous substitution, which means low negative charge, which means, of course, low cation exchange capacity, or not many exchangeable cations can be absorbed on this type of clays. Kaolinite crystals are larger than most other clays. Why? Why are they larger? The reason they are larger because many crystal units or layers can stay together because they are held by strong hydrogen bond. So the possibility of finding so many of them together in nature more than other minerals. That's why the crystals, which is made of so many crystal units, are larger than most other clays. In contrast, that's comparing the opposite. In contrast to some 2-to-1, which we will study later, silicate clays, 1-to-1 clays like kaolinite exhibit less plasticity, thickness, cohesion, shrinkage, and swelling, and can also hold less water than other clays. All these properties, plasticity is the ability to be formed. If you hold it with your hand when it's wet, you can form it in different shapes. Thickness, how much it sticks to your hand, to other things, and the cohesion, how much it sticks to each other within the clay itself. Shrinkage and swelling we talked about. So, in contrast to 2-to-1, if we compare the 2-to-1, all these properties are low because it has low surface area, low capability of holding so much water. So all of these characteristics will be low. Kaolinite containing soils are well suited for use in road beds and building foundations. If your soil, if you're gonna build a building or build a road, and you have the soil which has kaolinite, you don't have to worry about removing it because you can build right on it. there will be no expansion and shrinkage. So you don't expect these structures on top of it to crack or to anything will happen to them. So they are okay to build on them roads and foundation buildings or anything. The non-expanding one-to-one structure also makes kaolinite clays useful for making bricks and ceramics. Because of this, when you see all the pots and zir wal gawawir and all what you see on the roads and people use them a lot, they are made of this type of clay because they don't crack. Otherwise, if you make them from any other that expands and shrinks, they will not last. They will break when they do. So this finishes the one-to-one. In our next lecture, we will start talking about the two-to-one.